In this lecture, we'll discuss symmetries in graph. So a graph, it may be symmetric about x-axis or y-axis or about origin, or it may have symmetry about x equal to a line. Suppose I'm given a relationship between y and x as y equals fx, and I need to find whether the graph is symmetric about x-axis. All I need to do is I'll need to replace a y with minus y, and if the equation is unchanged, then the graph is symmetric about x-axis. Say for example, y square equals 4ax. Now if I'll replace y with minus y, then equation remains the same. So that means this graph is symmetric about x-axis. And we know that it's a parabola of the first form, right? So which clearly is symmetric about x-axis. Now for y-axis symmetry, replace x with minus x, and if equation is unchanged, then the graph is symmetric about y-axis. Say for example, y equals 2x square. So if I'll replace x with minus x, again it will be the same equation. So this graph is symmetric about y-axis. Now y is equal to 2x square is again a parabola opening upwards. So again, this function is symmetric about y-axis. Now the third symmetry that we'll study is origin symmetry. Now for origin symmetry, we'll replace x with minus x and y with minus y. And by replacing x with minus x and y with minus y, if the equation is unchanged, then we'll say it has an origin symmetry. Say for example, y equals sine x. Now if I replace y with minus y and x with minus x, I'll end up getting the same equation, which is y equals sine x. So that is, the graph of sine x has origin symmetry. So that means it is symmetric in opposite quadrants. That's the graph of sine x. So it is symmetric in opposite quadrants. So it does have an origin symmetry. Now, if a function is symmetric about x equal to a line, then in that case, fa minus x should be equals to fa plus x. Or if I replace x with x minus a, I can also write it as fx should be equal to f 2a minus x. Now say for example a function is given as fx equals 2x minus x square. So I know it's a quadratic expression opening downwards, the roots at 0 and 2. So if I'll draw this graph, I clearly know that it is symmetric about x equal to 1 line. So if I find f 2a minus x, which in this case will be f2 minus x, I'll get (2x minus x square), which is same as fx. So from here also I can say this graph will be symmetric about x equals to 1 line. Thank you. In the previous lectures, we have studied how to draw interesting and stunning graphs using transformation. Now today we'll study how to draw them using curve tracing. Now curve tracing, it does involve lot many steps, but then at the end you'll get comprehensive and elaborate graphs. Now there are 8 steps in curve tracing which will help us to draw a freehand sketch of a given curve. So we'll start with domain of the function, and then we'll discuss if there is any symmetry in the function. Thereafter, we'll go to its continuity and differentiability. Then we'll look for all the points of intersection where the curve intersects x-axis or y-axis. Then we'll look for the interval where this function increases or decreases. Thereafter, we'll find points of maxima and minima, and we'll also find out their maximum and minimum values. 7th point is we are going to differentiate it twice to discuss its concativity and its points of inflection. So 7th step is actually an optional step. So if there is a pressing requirement to find concativity or points of inflection, I'll go for the 7th point, else I may skip it. And 8th is I'm going to find the limits at the start and end of the given interval which we have got in domain. And then finally, I'll draw a freehand sketch. So I'll take an example. Say, for example, a function is given as fx equals 2x upon 1 plus x square. Now for this function, I cannot draw this graph using transformations because there is no basic curve with which I can draw this graph. So I'll go with curve tracing. Now the first step is to find its domain. Now in order to find domain of this function, I'll need to identify if there is any restriction in the function. So the only restriction that I can see here is denominator should not be 0. So 1 plus x square should not be 0. Now 1 plus x square is always greater than 0 for all real values of x. So that means domain of this function will be x belongs to R. Now we'll discuss symmetry in this curve. We have already discussed symmetry in one of the previous lectures. So what I'll do is I'll replace y with minus y and x with minus x. And when I do that, I end up getting the same curve. That means this curve is going to have an origin symmetry. This graph will be symmetric in opposite quadrants. Now, third thing that we need to discuss is its continuity and differentiability. I see two polynomial functions, 2x and 1 plus x square. Both the functions, they are continuous and differentiable, and also denominator cannot be 0. So this given function will be continuous and differentiable for all x belongs to R. So my graph will be a connected graph and there won't be any sharp corners or edges. Everywhere it is going to change the shape smoothly. Now the fourth step is I need to figure out the points where this curve is going to intersect x-axis and y-axis. So if I'll put x as 0, I will get y equals 0. And if I'll put y equals 0, again I'll get x equals 0. So the only point where this curve is going to intersect x-axis and y-axis is origin. And other than that, it will never intersect x-axis and y-axis. Now for intervals of monotonicity, I'll differentiate the function. I will put it equals to 0 and then I'll find its critical points. So critical points here are minus 1 and 1. I'll place them on a number line. Now here coefficient of x square is negative, so it will be minus, plus and minus. It clearly means this function will be decreasing when x is greater than 1 or when x is less than minus 1, and it will be increasing between minus 1 and plus 1. Now we'll also find its points of maxima and minima. So the critical points are minus 1 and 1. Now at minus 1, the sign of derivative changes from minus to plus. So that means this minus 1 is a point of local minima. And for 1, the sign changes from plus to minus. That means it's a point of local maxima. So for minus 1, the graph first decreases and then increases. So obviously it's a point of local minima. And at 1, the graph first increases and then decreases. So that means, so at 1, there's a local maximum. I will also find the values at minus 1 and 1. So if I'll put x as minus 1, I'll get minus 1. And if I'll put x as 1, I'll get y as 1. Now for this graph, I actually don't need concativity and points of inflection. So I'll skip step number 7. I'll straight away go to step number 8, which is to find the limits at the start and end of the given interval. Now domain of this function is x belongs to R. So this graph, it will start from minus infinite. So I'll find this limit. So limit x tends to minus infinite, 2x upon 1 plus x square. Now degree of the numerator is less than degree of the denominator. So that means the limiting value of this function at minus infinite will be 0. In the same way, I can find limit when x tends to plus infinite, and there will be 2x upon 1 plus x square. Now this again will be 0. So now we'll summarize the entire information which we have got from these steps. So domain of this function is x belongs to R. So this graph will be drawn from minus infinite to plus infinite. It has an origin symmetry, so graph will be symmetric in opposite quadrants. It is continuous and differentiable for x belongs to R. So this graph will be a connected curve and it will always change smoothly. The only point where it will intersect x-axis and y-axis is origin, and other than that, it will not intersect x-axis or y-axis. Now, fifth one is interval of monotonicity. So between -1 and +1, it will be an increasing function, and when x is less than -1 or when x is greater than 1, it will be a decreasing function. It will have a local minimum at x equal to -1, and it will have a local maximum at x equal to +1, and their values are -1 and +1 respectively. Seventh step, I've skipped in this graph. Since the domain is x belongs to R, so at -infinite and +infinite both, the value of this limit is 0. So now we'll draw a freehand sketch. Domain x belongs to R, origin symmetry, continuous and differentiable in x belongs to R. So intersection with x's. So the first point that I'll mark on this graph is origin. So this graph, it must pass through origin. Now then I'll mark critical points. So the critical points are -1, +1. Now at -1, there is a local minima and the minimum value is -1. So at -1, I'll also mark this value. And because it's a local minima, so I'll draw it like that. Now at +1, the value is 1 and it's a local maxima, so I'll draw it like that. Now between -1 and +1, it's an increasing function, and before -1 and after +1, it will be a decreasing function. Now we'll come to limits at start and end of the given interval. For both the limits, the value is 0, so that means this graph, it approaches 0 when x is -infinite or +infinite. So I'll start drawing the graph. So it'll start from 0, then it will decrease, it will take a minimum value at -1, and then it will pass through origin, and then it will take maximum value at +1, and then it will again decrease, and finally the value will be 0. So that is the graph of 2x upon 1 plus x square. Let us take another example. So the function is ex into ln ex. Now the first thing, it's domain. So for logarithmic function, ex should be greater than 0, x should be greater than 0. So domain of this function will be x belongs to 0 to infinite. So this graph, it will be drawn from 0 to infinite. Now I cannot put -x in that. So there is no symmetry in this given curve. In the interval 0 to infinite, both the function ex and ln ex, they are continuous and differentiable. So this function is continuous and differentiable in x belongs to 0 to infinite. Now the fourth step is to find the points where it will intersect x-axis or y-axis. I cannot put x as 0 because it is not included in the domain. So if I'll put y as 0, I'll get ex ln ex. So that means I'll get ex equals 1, x equals 1 upon e. So that means it will intersect x-axis at 1 upon e comma 0, and it will never intersect y-axis. Now fifth step is I'll differentiate the function. I'll find dy by dx. I'll put it equals to 0. I'll find critical points. I'll mark the point on a number line. Now when x is greater than 1 upon e square, 1 plus ln ex will be positive, and before that it will be negative. So that means from 0 to 1 upon e square, it will be a decreasing function, and then after 1 upon e square, it will be an increasing function. Now at 1 upon e square, the sign changes from minus to plus. So that means 1 upon e square is actually a point of local minima. So I'll also find the value at 1 upon e square. So if I'll put x as 1 upon e square, I'll get minus 1 by e. Now again, I'll skip step 7. So I'll straight away go to my limits. Now here, because the domain is from 0 to infinite, I'll need to find this limit. Limit x tends to 0 positive ex into ln ex. So the first thing that we'll do in any limit is to find its form. Its form is 0 and ln 0 is minus infinite. So it is 0 into infinite, which is an indeterminate form. So I can write it as limit x tends to 0 positive. I can write it as e ln ex upon 1 upon x, which is infinity upon infinity form. Now I can use D L'Hospital rule. So I'll differentiate numerator and denominator separately. So limit x tends to 0 positive. So it is e 1 upon ex and then into e, and this is minus 1 upon x square. So if I'll solve it, I'll get this limit as 0. So when x tends to 0, the limiting value of this function is 0. I'll also find limit at x equals infinite. So which is ex into ln ex. Now when x tends to infinite, it is infinite, and log infinite is also infinite. So infinite into infinite is infinite, which is not an indeterminate form. That means the limiting value of this function when x tends to infinite is infinite itself. Now I'll start drawing the graph. So I've drawn the axis. Now first thing, domain is from 0 to infinite. So this graph will be drawn from 0 to infinite. There is no symmetry in the graph. So it is always be connected, and it's a smooth graph. It will intersect x-axis at 1 upon e. So I'll mark this point. Now I'll mark this critical point, which is 1 upon e square. So 1 upon e square, it will be before 1 upon e. So I'll mark this point as 1 upon e square. Now between 0 and 1 upon e square, it will be a decreasing function, and after 1 upon e square, it will be an increasing function. Now it has a local minima at 1 upon e square, and local minimum value will be minus 1 upon e. Now limiting value at 0 is 0. I'll put an open circle at 0, and then I'll start drawing the graph. So between 0 and 1 upon e square, it will decrease, and it will have a minima at 1 upon e square. It will pass through 1 upon e, and then it will go up to infinite. So that is the graph of ex ln ex. Now the next question is y equals e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x. First, domain. Domain is x belongs to R because denominator cannot be negative and there is no other restriction. Secondly, so if I replace y with minus y and x with minus x, take minus common from the right hand side, I'll end up getting the same function. So that means this graph will have origin symmetry. So it will be symmetric in opposite quadrants. It is continuous and differentiable in x belongs to R. Now if I'll put x as 0, I'll get y equals 0. And if I'll put y equals 0, again I'll get x equals to 0. So that means the only point where it will intersect the axis is origin. Now I'll differentiate the function. So if I'll differentiate, I'll get 4 upon e to the power x plus e to the power minus x whole square, which is always greater than 0. So that means this function is increasing in x belongs to R and there are no critical points. So that means this function, it doesn't have a local maxima or local minima. So if I'll put this second derivative equals to 0, I'll get x equals 0. So x equals to 0 is point of inflection. Now I'll find the limiting points. So limit x tends to minus infinite. So first I'll identify the form, and the form is infinity upon infinity. Basically minus infinity upon infinity. Now if I'll divide it with e to the power minus x, I'll get limit x tends to minus infinite e to the power 2x minus 1 upon e to the power 2x plus 1. So answer to this limit will be minus 1. In the same way, if I'll find limits at plus infinite, form is infinity upon infinity. If I'll solve it, I'll get this limit as plus 1. So now I'll start drawing the graph. So I'll draw the axis. Domain is x belongs to R. It will have an origin symmetry. It will be connected and smooth. it will intersect x-axis and y-axis at origin. It will always be an increasing function. Then at 0, there is a point of inflection. Now at minus infinite, this value is minus 1. So that means I'll draw a horizontal asymptote at minus 1. And at plus infinite, the value is 1. So I'll also draw a horizontal asymptote at y equals to plus 1. Now I'll start drawing this graph. So it'll start from minus 1. Then it will increase. It'll pass through 0. It'll change its concativity at 0. Then again it will increase. And at plus infinite, it will be again 1. So that is the graph of e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. Now the fourth question is, draw the graph of y equals x square into e to the power minus mod x. Now for this function, first I'll find domain. So there is no restriction in the function. So domain obviously is x belongs to R. If I replace x with minus x, I'll get, which means this graph has a y-axis symmetry. Now the third thing is, we need to discuss its continuity and differentiability. Now it is continuous and differentiable in x belongs to R. Actually, I need to check the differentiability at 0 because we do have mod of x. But then when you'll find left-hand derivative and right-hand derivative, you'll find that it is differentiable at x equal to 0. Now the fourth step is to find points of intersection. So if I'll put x as 0, I'll get y equals 0 and there is no other point of intersection. So the only point where it will intersect x's is 0, 0. Now because this graph has a y-axis symmetry, so what I'll do is, I'll draw the graph when x is greater than or equal to 0 and then I'll replicate the same graph on the left hand side. I'll write this function as y equals x square e to the power minus x when x is greater than or equal to 0. I'll find dy by dx. So if I differentiate the function, I'll get dy by dx as e to the power minus x, 2 minus x and plus x. So the critical points are 0 and 2. So 0 and then it's 2. Rightmost it is minus, so this is minus and this is plus. So between 0 and 2, this function, it will increase and from 2 to infinite, it will decrease. Now at 0, it will have local minima and at 2, this function will have local maxima. I'll also find this value. So now if I'll put x as 0, I'll get y as 0. And if I'll put x as 2, I'll get y as 4 into e to the power minus 2. Now I'll find the limits also. Now because I'm taking the reflection of right on left, I'll just need to find one limit, which is limit x tends to infinite. So I identify the form infinite e to the power minus infinite is 0, which is an indeterminate form. So I'll write it as x square upon e to the power x, which is infinity upon infinity form. So if I'll differentiate it twice, I'll get this limit as 0. So now I'll draw my graph. So it'll intersect x-axis and y-axis at origin. Local minima at 0, minimum value 0. Then at 2, maximum value 4 upon e square. And then at infinite, it will be 0. So I'll draw this graph. And now because it is symmetric about y-axis, I'll take the reflection of right on left. So that is the graph of y equals x square into e to the power minus mod x. I can write fx as x plus under root of minus x when x is less than 0 and x plus under root of x when x is greater than or equal to 0. So if I'll differentiate this function, I'll get, now this function is not differentiable at x equal to 0. So x equal to 0 is one of my critical point. And also, if I'll put f dash x equals to 0, I'll get x equals minus 1 by 4. So there are two critical points, x equal to 0 and x equals minus 1 by 4. So I'll put them on a number line. So rightmost it is plus, then minus, and then plus. So it will be increasing when x is less than minus 1 by 4, decreasing between minus 4 and 0, and then again increasing when x is greater than 0. At minus 1 by 4, it will be a point of local maxima, and 0 is a point of local minima. The value at minus 1 by 4 is 1 by 4, and the value at 0 is 0. I'll also find limits. Limit x tends to minus infinite fx will be minus infinite. Limit x tends to infinite fx is plus infinite. So I'll mark these 2 points, 0 and minus 1 by 4. So at 0 it is 0, and at minus 1 by 4 it is plus 1 by 4, and it's a local maxima. If I'll put fx is 0, I'll get x equals minus 1. So it'll pass through minus 1. So its graph will be starting from minus infinite. It'll take local maximum at minus 1 by 4. At 0 it is not differentiable. So that is the graph of x plus under root of mod x.